Moisture and Precipitation Process. Chapter 4 involves 3 lectures. We're going to start with humidity and condensation process. That's lecture number 1 of the 4. And what we've got is a figure showing the 3 states of water: the liquid state, the solid state, and the gaseous state. And it's showing the phase changes. Now, of all of the phase changes between these 3 states, we're going to be concerned with just one of these phase changes, and that is condensation. What we want to learn is how we go from moisture in the air, humidity, or just water vapor, and how we go from moisture in the air, humidity, and condense it into liquid water droplets, making a cloud and ultimately precipitation. That's what we're going to be working on in this lecture. So let's begin by defining humidity. It's the amount of water vapor, or simply moisture, in the air at different temperatures. So we already know, humidity is moisture in the air. We certainly know that in Louisiana. But there's a very important relationship between the amount of water vapor the air can hold and temperatures. And this is the relationship. As temperatures increase, air's capacity to hold water vapor also increases. So at the top, we've got temperature in Fahrenheit, from very cold to very warm. And on the vertical, we've got the amount of water vapor in grams. And we're just going to start with no water vapor to a lot. And we can see that at cold temperatures, say maybe, maybe 15 degrees, the air can only hold 2 grams of water vapor. And then increasing maybe to maybe about 68 degrees. Warmer temperature, we can hold more, 15 grams. At about 85 degrees, it's warmer temperature, 26 grams. All right. So what we say in general is that, cold air, and progressively colder, has a small capacity, can't really hold that much water vapor. And then conversely, warm air, and progressively, the hotter the air is, the larger capacity. And it all has to do with, cold air contracts and can't hold as much, and warm air expands, and so it can hold more. But the thing is, I've got Louisiana and Phoenix here. Both states are very, very hot in summertime. We're usually here, in the 90s. And so we have a large capacity to hold water vapor. We can, in this diagram, in the mid-90s, hold about 35 grams of water vapor. And so we can hold, 10 grams, 20 grams, 30, up, to a maximum of 36 grams. So that's a lot. And, well, Phoenix, it's even hotter. You've seen temperatures of Phoenix, 110 degrees, what have you. But it's a desert. And so the question is, Phoenix has even a greater capacity. It's hotter. It has an enormous capacity, well over 50 grams that it can hold. And why is it a desert? And the answer is the Gulf of Mexico. Louisiana has a source of moisture to fill in our large capacity. And so we're constantly evaporating water from the Gulf of Mexico and filling in our large capacity. And so we typically have high humidities. Right? We've got a high moisture content because we have a source of moisture. Now, even though Phoenix has even a greater capacity, it has the desert of Mexico to the south of it. And so even though it has a huge capacity, it's never filled up, or rarely filled up. What we want to do now is take a look at this green line, and this is called saturation point. And saturation represents the maximum amount of water vapor the air can hold at different temperatures, the absolute maximum amount. And the important thing about saturation, once you filled up, let's just take about 85 degrees, once you filled the air up to capacity, that is the point where you have the phase change. you filled it on up, and then what happens is you add more water vapor evaporating, and the air simply can't hold it. And so you wind up condensing that extra amount of water that's evaporated. So saturation point, all right? So you've got to fill the air up to capacity and then add more water vapor, and you'll wind up with that phase change. All right, there's a term that you're very commonly shown on TV weather, and it's called relative humidity, and it's often abbreviated as RH, as a percentage. Now, the important thing, that percentage shows you how close the air is to saturation, right? And to, how close we're going to get to actually having the phase change from, the gaseous state to actual liquid water droplets. Now, I'm going to show you the simple calculation, but again, remember the percentage is showing you how close you are to saturation, how close you are, all right, to get, maybe dew or fog or clouds. What you do is, I've got an example here too, but anyway, what you do is you take the actual amount of water vapor in the air, and you divide it by the saturated amount, the maximum amount it can hold, and you multiply that by 100 to get a percent relative humidity. Now, I've got an example here. We're going to pretend you've got to know the temperature outside, right? Because the saturation point is very much related to temperature. So we're going to pretend that it's 85 degrees outside, all right? And we're going to pretend that the actual amount of water vapor in the air is 13 grams. I've got this worked out perfectly and easy. And we can see that the saturated amount, the maximum amount the water in the air can hold, is 26 grams. So this is going to work out pretty easy. Can you see, all right, that we're right now holding half of what is needed to reach saturation and ultimately condensation? So are we anywhere near capacity? No, right? We're only half there. And so there's the calculation. So the actual amount divided by the saturated amount, you wind up with 0.5, multiplied by 100 to get 50%. So how close are we to saturation? We're only holding half, all right? So we're nowhere near getting dew or fog or a cloud, all right? 50%. Now, let me give you another example. Okay, we're still at 85 degrees, and let's say the actual amount of water vapor in the air at 85 degrees is 26 grams. Well, we see the saturated amount is also 26 grams. And so what we're going to wind up with is the actual amount divided by the saturated. We've reached saturation, and so we're going to have 100% relative humidity. And so, again, what we need is to reach saturation, all right? And that's the beginning of condensation. You add more water vapor, and you will continue to condense. All right, so there are two ways to reach saturation. The first way is something that I've already been talking about, evaporation from the oceans, and in our case for Louisiana, mostly the Gulf of Mexico. But it's a relatively slow process. Gradually over days, you've got this slow evaporation, into the air, and gradually, relative humidity is increasing and increasing and increasing, and so to the point where you get up to 100% relative humidity. But usually it takes days. All right, so on any one day, the amount of moisture in the air doesn't change that much. But there's another way, a much more important way, and I've got this, highlighted. A very, very fast way to reach saturation is to change the temperature. And you can do this in hours, a couple of hours, not days. You change the temperature. And you change the temperature, and it's all related to the fact that cold air can't hold much water vapor, and warm air can hold a lot. And so this is the most important statement of this entire segment in Chapter 4. All right, of all 4 topics, you've got to know this. You get this ingrained in your brain. All right, you lower the temperature, you increase relative humidity. Lower the temperature, increases the relative humidity. That is the key to understanding how you get clouds, how you get fog, and how you get ultimately precipitation. And so what we're going to do is we're going to lower the temperature in a day. You know, as you know, that we've got the warmest temperatures usually in the afternoon, and then, you know, temperatures decline overnight, and, you know, by sunrise we have our lowest temperature. So we're going to have kind of an extreme example here. So we're going to start with 85 degrees, all right? And so we're going to just round off 26 grams to 25 grams. But all right, so what we're going to say is during this day, all right, and we're going to lower the temperature from the high to the low of the day. We're going to say that during this day, the amount of water vapor in the air is 5 grams. So it's not changing that much. It doesn't really change, you know, that much during the day. And what we're going to do, and what changes a lot during the day, is the temperature. So let's get our relative humidity in the afternoon. And if we're holding 5 grams, but the maximum amount that we can hold, the saturated amount, is 25 grams, let's just say for simplicity. And so you got the actual amount divided by the saturated amount is 0.2, multiplied by 100 to get relative humidity. So in the afternoon, you know, you can see by the graph, I mean, we're not holding anywhere near as much water vapor to reach saturation. So we're only holding 20%. 20% relative humidity. Now let's have a really dramatic drop in air temperature. It's kind of an extreme example. But now let's drop the temperature to 30 degrees. Now it's colder out, and so cold air has a smaller capacity to hold water vapor. And so we're really going to have a major drop in the air's capacity to hold water vapor. But what doesn't usually change that much is the amount of water vapor in the air. So now we've got a dramatic drop in temperature overnight. And so we're going to say, in this example, we're dropping to 30 degrees Fahrenheit. And so, well, our actual amount of water, the amount of water vapor in the air is 5 grams, staying about the same. But now, this colder temperature of 30 degrees can only hold 5 grams of water vapor. So that's our saturated amount. And so what we've wound up doing by dramatically, in this case, lowering the temperature, we've increased the relative humidity. We've increased the relative humidity to the point where we've actually reached saturation. And so now we're holding the maximum amount of water vapor the air can hold, and that's when we have our phase change to dew, to fog, to clouds. All right. So saturation means 100% relative humidity, and that's very important for everything we're going to do from now on. Now, of course, the opposite is true. If you increase the temperature, you're going to wind up lowering the relative humidity. And so, I mean, you can just do this in opposite. Increase the temperature during the day, and you're lowering the relative humidity because warm air has a larger capacity. Let me show you this in a different way, in a figure from the textbook. What we're showing is 3 times during the day, 4 a.m. where it's cold, 41 degrees. It's warming up to 61 degrees by 10 in the morning, and then by 3 in the afternoon, usually about the warmest temperature of the day, is 90 degrees. And so what we're showing here in a blue box is the certain amount of water vapor in the air, moisture in the air on that one day. See, it's not changing at all right? But what does change is the capacity of the air to hold that water vapor. And so when it's cold out, we have a small capacity, and so usually our relative humidities are going to be pretty high. And so in the morning, when we have the lowest temperatures of the day and the smallest capacity, we're going to have our highest relative humidity. They're usually around here, 70, 80, 90, or even 100, okay? And once we have 100% relative humidity, I mean, that's where we're going to have foggy mornings, and, dew is going to form on your car and on the grass. And then as temperatures increase, well, you can kind of see here, as they're showing, right here at 10 a.m., we're holding half of what we potentially could. And so you can see we're only at 50%, and then In the afternoon, we've got a very, very large capacity, but we're still holding that little blue box, that same amount of water vapor, and we've reduced relative humidity to 20%. So usually in the afternoon, when we have our highest temperatures of the day, we have our lowest relative humidity. So this is kind of an inverse relationship. You know, when you've got the lowest temperatures of the day, you've got the highest relative humidity. When you've got the highest temperatures of the day, the lowest relative humidity. What we're going to do now is introduce one other term, and it's called dew point, and we're going to abbreviate it DP. It is the temperature in the atmosphere where saturation occurs, where we reach 100% relative humidity. So dew point is actually a temperature. We call it dew point temperature. And it's a certain temperature where the air reaches 100% relative humidity. I know that means nothing to you right now, but I want to give you an example, an illustration, to illustrate what dew point actually means. And I want to just take a really typical steamy hot summer day in South Louisiana, in Thibodaux. And what I want to show you is a built-up area, you know, NSU campus, you know, with buildings and parking lots, asphalt and rooftops and concrete and what have you. And then we want to compare this built-up area to, you know, a more natural green environment, you know, the swamp or the marsh or sugarcane fields. And what winds up happening is, you know, certain surfaces on the ground heat up faster than others. And literally, what winds up happening in the atmosphere, you know, above this superheated surface, we actually create a bubble of heated air. A bubble, that's what we imagine, a parcel or a bubble of heated air, and we call it a hot spot. All right, a hot spot. Now, what does hot air do? All right, hot air expands, becomes less dense, and it rises. So this bubble of air is going to start to rise. All right, and what we call rising air in the troposphere, they're called thermals. All right, thermal being warm. So we've got these, you know, heated bubbles of air rising, and they're called thermals. All right, so we've got our hot spot, our heated bubble of air, and it's going to form over the superheated ground. All right, and so now as it's rising, it's called a thermal. Now, if you've ever flown in airplanes, I mean, you go on a hot summer afternoon, I mean, when you're taking off, it's very, very bumpy. And it's really so, the thermals are moving so rapidly, they can be moving 100 miles an hour, that they can actually cause, you know, turbulence or bumpiness in an airplane. And even another example is like soaring birds, you know, that they're just gliding along without flapping their wings, and they're just catching one thermal after another. So usually there's, you know, hundreds of thousands of thermals rising in any one area. Now, the important thing, all right, is as this thermal is rising, it is cooling. Remember this important relationship that we learned for exam 1. Temperatures decline in the troposphere. So as this heated bubble of air is rising, it's cooling. We're cooling inside this bubble of air. Now, we got to go back to the most important little statement of this entire segment. All right? What did we state? You cool the air, you increase relative humidity. It's because cold air has a smaller capacity to hold water vapor, and you're going to increase relative humidity. And so what's going to happen inside this bubble of air as it's rising at, you know, 1,000, 2,000, 3,000 feet? We're cooling the air inside this bubble of air, and we're increasing relative humidity. All right. Now, what's going to wind up happening is typically, you know, on a typical steamy afternoon, you know, usually relative humidities at the ground are in this 65 or 70, something like that. And what's going to wind up happening as you're cooling this bubble of air from 65 or 70% relative humidity, you're going to be increasing it to, you know, 85, 90% relative humidity, you know, still cooling. And at the point in the atmosphere where we've reached saturation, 100% relative humidity, we've reached dew point temperature. All right, and there we are here. So we've cooled the air, all right, and we've increased relative humidity, say from 65% relative humidity at the ground, and we've cooled the air, so we've increased relative humidity to 100%. We've reached saturation point, and so the air, at whatever hot temperature it is, has reached the maximum amount of water vapor it can hold, and we've still got more water vapor being added to that temperature, and so we're going to start condensing. And so what we wind up is a certain temperature. For us around here, it's usually in the 70s. All right, so we're usually cooling air at least 20-25 degrees as it rises thousands of feet in the air. And what we're going to start to do is go from moisture in the air, all right, and we reach 100% relative humidity. We got that phase change, all right, and more water vapor is added, and we're going to continue with condensation. And what we're going to see is the beginning of a cloud, all right? And when we condense, all right, we're not creating giant water droplets. We're creating tiny water droplets in the cloud. And tiny water droplets are just what they are. They're minute. They're like the size of a pinprick, all right? And this is the technical term for them. They're called tiny water droplets. And it's very often that you see clouds forming at the exact same elevation, all right, in the atmosphere, because that's the air temperature where all of these hot spots have reached 100% relative humidity. Now, do all clouds form rain? No. What you need is time, and you need time for those thermals, those rising bubbles of air in the cloud, all right, to coalesce. You've got these little tiny water droplets, and they're rising maybe at 100 miles per hour, and what they're doing, these little tiny pinpricks are starting to join or coalesce. And as you move, 1,000, 2,000, thousands of feet, making this cloud, these tiny water droplets are joining or coalescing. And my cloud is kind of tiny, but you've seen towering clouds, and usually by the time you've made a cloud towering, 10,000 feet tall, you've taken these tiny pinpricks, right, and you've coalesced or joined them in the rising air. They're just banging into one another until you wind up creating a raindrop, right, that's heavy enough now to fall, right, being pulled by gravity, right, back down to Earth, right. And so there's my raindrop falling back down to Earth. If you think about how tiny water droplets are, they're so tiny that they defy gravity, right? They can actually remain suspended in the air, and so you need them to coalesce, that's the term, in the cloud, and become big enough to fall as rain, right? And so that's what dew point temperature is. All right, here's a figure just kind of illustrating what we're talking about. We've got a hot spot and a thermal, all right, and a heated bubble of air. And they've got it here as a windy day. So they've kind of, pulling our bubble of air downwind. But normally it would rise, all right, and it would cool, and relative humidity would be increasing until it increased to 100% as you cooled the air. And once you cool the air reaches 100% relative humidity, and you're going to have that phase change. You fill the air up to capacity, and any more water vapor that's added winds up condensing and forming a cloud. And there we got there. And so it's so typical around here, particularly in summertime, but really any time of the year. And usually you have to be kind of looking at a distance. Maybe you're driving on the road and you just kind of look at the sky in the distance, and you'll notice that all the clouds are forming at the exact same elevation. And they have flat bases, flat cloud bases. And you've got a little perspective here, but that's telling you that that's the dew point temperature. And usually around here in summertime, when it's 90 something, at the ground, dew point temperature is usually in about the 70s. So you've got to, get the air to rise and cool, usually about 20-some degrees in summertime. And again, we've got the perspective. When you're flying in an airplane, you can actually see all the clouds forming at the same elevation, dew point temperature, and you just look at them all, right? I mean, there's literally millions of thermals rising. Right. And so you can actually feel them when you're flying in an airplane, if they're rising at a very rapid rate. We're going to move on to one little final topic in this lecture, number 1, and talk about fog. Right. I've just kind of shown you how clouds form at, a couple thousand feet by getting that air to rise and cool. Now, fog is nothing more than a cloud at the Earth's surface. And so in order to create fog, what we've got to do, all right, instead of lifting the air in the troposphere and cooling it, what we've got to do is we've got to chill the air, all right, at the ground surface, so we reach dew point, 100% relative humidity at the ground, instead of, getting hot spots rising and cooling and getting a cloud at a couple thousand feet. And there are 2 major ways to excessively chill the ground surface so that you can chill the air and increase relative humidity to 100% at the ground. All right. And so there are 2 ways. And here we've got my definition of fog. You've got to cool the air to dew point temperature at the ground, all right, instead of, getting it to rise in the troposphere. And there are 2 major ways. There are 2 types of fog. And the first one that I want to introduce you to is called radiation fog. And this is by far the most common type of fog. This is what we get. Whenever we have fog, this is what we get. It's called radiation fog, but it's because it's referring to the loss of long-wave radiation overnight. Remember, that's the Earth's heat that it gives off, starting in the afternoon and all night long. And so by definition, it's when you have the excessive loss of long-wave radiation overnight. And what you've got to have, all right, in order to completely chill the air and have a very cool overnight, is you've got to have clear overnight conditions. Right. Now, if it's cloudy, remember, clouds act like a blanket and keep the temperatures warm at the Earth's surface, so you won't have fog then. But you need clear overnight conditions so you can have all of that long-wave radiation escape to space, and you'll actually excessively chill the ground surface, and you'll wind up reaching dew point. Now, it can't be very windy out, otherwise condensation can't occur. And you've got to have some moisture in the air. I mean, so you'll, cool the temperature a few extra degrees, just those few extra degrees to, increase, relatively moist air to 100% relative humidity. So, a lot of times, a cold front moves through and, and we get Canadian air and it's dry. And so we won't have fog, the next morning or 2. But usually, by the 3rd morning, winds start to turn around and we start to get a little bit moisture in the air from the Gulf of Mexico. And usually by the 3rd or 4th or 5th night, we've increased moisture in the air, even though it's still, clear overnight. That will chill the air, and now we've got finally enough moisture in the air and we'll start to get radiation fog. Now, this is kind of a pretty cool picture of radiation fog from the air, because what is it? What is fog? It's nothing more than a cloud that is formed at the ground, and that's what we're illustrating there. Now, the other type of fog is called advection fog. It is when you've got warm and moist air. All right, and so you've got to have warm air that's holding a fair amount of moisture. Remember, warm air can hold moisture, and you've got to chill that air. All right, you move it over a cold surface. All right, and cold air can't hold much moisture. Cold air can't hold much moisture, so you'll increase relative humidity to 100% to dew point. And advection means a horizontal movement of air. That's what advection means. And I've got the example, very common place that is very, very foggy, and the type of fog that it receives is advection fog. Fog City, that's actually the nickname for San Francisco. It has so many fog days per year. But even Portland and Seattle, a lot of cities along the west coast of the United States receive advection fog. Now, what I'm illustrating on this diagram is advection. We've got the westerly winds, of middle latitudes, the westerly winds that dominate the United States, and we've got warm water, of the Pacific Ocean, and this is in summertime. This is when advection fog is really at its maximum in summertime. So you've got warm water and warm air above it, and you've got a source of moisture. So you've got warm and moist air, and that warm and moist air is advecting over, guess what, the cold California current on the west coast of the United States. And so this warm and moist air advecting, moving horizontally over the cold California current, chills on down, all right, and relative humidity is going to increase to 100%, and so that you have masses of fog, all right, that are common, that are very, very common throughout the year, but much more so in summertime because you've got warm water and warm air. In wintertime, it's less frequent because the air is cooler and it's already cooled, right? And moving over a cold surface isn't really going to do much. So you've got warm, moist air, and then you chill it. Advection fog is also common in the northern states in wintertime. So, you say you've got a snow-covered surface, and say a warm front is moving northward over the snow, and so you've got warm, moist air, say from the Gulf of Mexico, moving over a cold, snow-covered surface, and you'll create advection fog. And And the thing about advection fog is, it doesn't necessarily evaporate or burn off by mid-morning. You still got that warm air, usually all day long, moving over that cold surface, that cold California current or the snow. And advection fog could last all day long or days on an end, day after day. And so it is a bit different than radiation fog in terms of that. End lecture 1.